Hi everyone. Last time we talked about the volume of prisms and cylinders, and this time we're going to cover the volume of pyramids and cones. So remember, volume is like how much space is contained within the solid. So similar to the way that prisms and cylinders had the same overall volume formula, pyramids and cones have the same overall volume formula. Although again, you have to be careful because the base area you might have to calculate differently depending on what shape the base is. So if B is the area of the base of a pyramid or a cone, and H is the height of the solid, the cone or the pyramid, then the formula for the volume is 1/3 times the base area times the height. So if you were to take away the 1/3, that would be just like the formula for a prism or a cylinder. Because cones and pyramids come to a point, they don't contain as much volume. In fact, they contain 1/3 of the volume of a prism or cylinder that has the same base and height. So here we go. Here is an example where we want to find the volume of a regular hexagonal pyramid with a height of 8 centimeters. Each side of its base is 6 centimeters. So these things are labeled in the diagram over here. The height of the pyramid is 8 centimeters. Each side length side length of the base is 6 centimeters. So we're going to use the formula we learned. We're going to use the 1/3 base area times height, but our base is a regular hexagon. So we first have to calculate what's the area of this regular hexagon before we can calculate the volume of the solid. So this is what we do first. We think about the base and its area. Now, this is a tougher formula to remember, but the formula for the area of a regular polygon is 1/2 the apothem length, so that the apothem is like from the center to the middle of one of the sides. So it's this length right here. And then P is the perimeter, so the distance all the way around the shape. Okay, so the perimeter, not hard to figure out because there are 6 sides and each is 6 centimeters. So if you do 6 times 6, or if you add up 6 times, you get 36 for the perimeter. Now what's tougher is finding that apothem length. So what they tell us that's useful here for figuring out the apothem is each of, like if you split the hexagon into triangles, each of these is an equilateral triangle. Because like if you split 360 degrees into 6, that each angle here, central angle, is like is 60 degrees, and so basically you could split the hexagon into 6 equilateral triangles. So this is 6 centimeters because it's got to be the same as this side, which is 6 centimeters. And then you can split the equilateral triangle into 2 30, 60, 90 triangles, and you can use what we learned about special right triangles. One thing we learned is that the shorter leg length is half of the hypotenuse. So divide 6 in half, that's 3. And then the longer leg is, you can find that by doing the shorter leg length times the square root of 3. So 3 times the square root of 3 is our apothem right here. So we plug that in for the apothem. And then when you multiply this out, I guess the 1/2 times the 3 times the 36 is 54. And then you still have that square root of 3 hanging around, so 54 times the square root of 3. Okay, now we're ready to, now this is like the formula that we learned. Volume equals 1/3 the base area times the height. So we were told the height was 8, so that's why we plug in 8 for the height. We just found the base area, 54 times the square root of 3, and then this 1/3 is part of the formula. When we multiply this out, we get 144 times the square root of 3, which is approximately 249.4 centimeters cubed. Remember that for volume, our units are cubed units of some kind, so centimeters cubed in this case. A cone has a base radius of 3 inches and a volume of 24 pi inches cubed to find the height. So this is a little bit different. We're not finding the volume. We know the volume, and we're going to use it to find another dimension of the shape, the height in this case. But we can still use our formula. So volume is equal to 1/3 times the base area times the height. And let's fill in the things we do know. The base is a circle, and so we're going to use the formula for the area of a circle when we are finding B, the base area. So instead of writing it as the base area, because it's a circle, we can write it as pi r squared. That's the area of the circular base. Okay, the radius is 3, so we plug in 3 there. We also were told the volume was 24 pi inches cubed, so we plug in 24 pi right there for the volume. 3 squared is 9. 9 times 1/3 is 3, so this side simplifies into 3 times pi times h. And then what's useful is, well, this is 24 pi, this is 3 pi. If you divide 24 pi by 3 pi, the pi's cancel or divide to 1, and 24 divided by 3 is 8. So this means the height of our cone is 8 inches. Okay, a couple other examples, and then I'll let you try the homework, which is an exit ticket. Volume of pyramids and cones is still what we're working on. The extra example is find the volume of a cube with a cone removed from the center. The side of the cube, the diameter of the base of the circle, and the height of the cone are all 6. We'll remember that all those measurements are 6. So it's a cube with a cone removed. So we're going to find the area of the cube. We're going to subtract out the area of the cone because that was removed. And then that'll give us the volume we're looking for. So I addressed the cube first. A cube is a type of rectangular prism. So we're going to use the volume formula from last time because that's the volume, like the volume of a prism is the base area times the height. There's no 1/3 included in that formula when it's for a prism. So the base area, well, the base of a cube is a square, and so the area is 6 times 6, because both dimensions are 6 for the base. And then the height is also 6, because it's a cube. All the dimensions are the same. So then You get 216 for the volume of the cube. Now there's a cone that's been removed. So we'll worry about removing it in a bit, but first, what is the volume of this cone? The formula 1/3 is base times height is what we learned for today. That applies to cones and pyramids. The base of a cone is a circle, so that's why I use pi r squared instead of the base area here, because I knew that the base of a cone was a circle. So they told us that the diameter of the circular base was 6, meaning the radius is half of 6, which is 3. So that's how I got 3 for the radius. And then the height of the cone is the same as the height of the cube, which is 6. So when I multiply this out, 3 squared is 9, 1/3 of that is 3. 3 times 6 is 18, and so 18 times pi is the volume of the cone. Now we removed that cone from the cube. So here's the volume of the cube. Here's us subtracting out or removing the volume of the cone, and then to multiply this out, or like do this on a calculator, you would get 159.45 centimeters cubed. Almost done. Here's a question relating to I guess real life. So, pyramids are shapes we encounter in real life. Egypt's Great Pyramid of Giza is about 147 meters in height and has an area of the base of approximately 52,900 square meters. Mexico's Pyramid of Kukulcan, not sure if I said that correctly, has a height of about 30 meters and a base area of approximately 3,025 square meters. What is the approximate difference between the volume of the Great Pyramid of Giza and the Pyramid of Kukulcan? So I'll show you that right away, but we use our formula because it's a pyramid, so we use 1/3 times the base area times the height for each pyramid. Now, this question goes a little bit easy on us because they just tell us the base area straight out. We don't have to calculate the base area. They just tell us the base area of the one in Egypt is 52,900, so plug that in for the base area, and that the height is 147. And they just tell us that the base area is 3,025 for the one in Mexico, and the height is 30 meters. So when you multiply this out, and you do the subtraction, you get about, and this is just an estimate because these things aren't exactly pyramids, they're just very close to the shape of a pyramid. 2,561,850 meters cubed. Okay, those are all the slides. I hope that helped you understand how to apply this formula, which is for cones and pyramids. Make sure you're always thinking about which volume formula applies, because you may still encounter some prisms and cylinders, in which case you need to remember the formula from last time. Good luck, everybody. Please email me if you have questions, and have a good one. Bye.